Good afternoon, everybody. I'd like to introduce our speaker today. His name is Mr. Dennis Schneible from Ball Aerospace. Dennis originally received his Bachelor of Science from Oglethorpe University in 1963. He originally worked for the Department of Commerce as a physicist. He has been with Ball Aerospace for about 18 years. During the early 70s, he was temporarily assigned to Johnson Space Center in Houston to participate in astronaut training for the Skylab mission. He also supported the operational portion of the mission as a member of the Solar Physics Science team. Since 1975, he has been involved in new business and advanced development for tasks for Ball. In 1984, he was given his current assignment as Strategic Operations Manager for Space Stations and Commercializations. I'd like you to welcome Mr. Dennis Schneible.
Talk about Space Station, and I'd like to start out with the slide you've seen on the screen here when you came in. This is particularly appropriate today because those of you who have seen the morning paper know that today the Soviet Union launched what they're calling their space station. It's called Mir, M-I-R, means peace in Russian. And they have put a rather large spacecraft into low Earth orbit. We don't know how big it is or very many of the particulars of it yet, but you'll be hearing about it on the news tonight and in the days to come. But I hasten to remind people, and that's why this chart is up here, this was the first space station. This was Skylab. It was launched by the United States in 1973. It was not ever manned on a permanent basis, but there were 3 separate crews that went up. The first crew for a month, the second crew for 2 months, and the third crew for 3 months over a period of about a total of 9 months. Skylab had a rather fiery demise, as you may recall. There were some problems during the liftoff of Skylab which caused it to achieve an orbit that was other than optimal. And then for other reasons, one being that the shuttle program did not get to Skylab in time to reboost it. Skylab did re-enter and burn up in the Earth's atmosphere, and most of it landed in Australia. I think it was 83 or so that it came in. So Skylab was our first, but Skylab is gone, and now it's time to press on to other things. I thought I'd show you a few concepts of Space Station first. Most of these are from our friends at Martin Marietta Company. They developed a number of these early concepts during what was called a Phase A, or preliminary design phase of the space station, which was conducted in the early 80s, 81 or so. Ball at that time was a team member of Martin's, and we participated in these studies. I'll go through these rather rapidly. What I want you to notice here in particular is how compact these look. They look like they're all very close together. You can imagine that some of the telescopes on board might have a little trouble seeing around solar arrays and each other. And these tended to be the kinds of concepts that we saw in the beginning. Very tight, packed things. Usually big telescopes pointing out in all sorts of different directions. I'll show you another one here. This one, I guess that's probably upside down. Maybe it doesn't make any difference. This one features what looks like an external tank as its core. As you probably know, there is a theory that says with very little additional energy, it would be possible to let the external tank and the solid rocket boosters burn just a little bit longer on the shuttle and put these big external tanks into orbit. And once the external tanks were in a parking orbit, then you could later come along and put them together in a configuration like this and use them as the core of a space station. That's a fairly serious consideration, and there are a number of people that are thinking about that, but so far we really haven't seen anything other than theory. This one too looks fairly compact. Again, you see a lot of telescopes, different view angles. You see the shuttle down there in the corner. And the other thing that seems to be flying off there to the side, it's actually connected with a little beam. I don't know if you can really see that very well. That's a shuttle pallet. So if you can imagine, that thing is about 15 feet across, and the shuttle bay is capable of taking 4 of those into orbit at a time. So one thing you might see happen in the space station era is that pallets like this will be flown up in the space station, removed from in the space shuttle, removed from the shuttle and placed just like you see it here on the space station. It's another possibility. Here's another concept. This one shows an external tank sitting over there in a parking orbit, the sort of brownish looking tank there, and then another small free flyer off to the side. Again, you see this very tight, compact look. This is my own personal favorite. This one appeared, that one does have to be the other way around. This one appeared on the calendar of our cover of our calendar this year. And of course, it was a great delight to our parent corporation, which is the ball canning and ball jar people. We sent a model of this to our headquarters in Muncie, Indiana, and of course they thought it was the greatest thing since screw-on lids. But when we were discussing whether we should really use this as the cover of our calendar, it was decided that what we would do is make it clearly obvious that this was tongue-in-cheek. We were just teasing. So we wrote up things that describe this picture as saying these are modules that can preserve both the crew and its food, things like that. But the model does exist, and it's been sent around the country to a lot of different ball plants, and we've had a lot of fun with this. But there's more reason than that, just for showing you this. If you remove that center section where the modules are, you'll have a pretty good picture of what the European space station looks like, and it's called Columbus, as you probably know. And I'll have a little more to say about that later, but when you hear the word Columbus, I really don't have a good picture of it, but if you imagine this thing without those white jars on the side, that's about what Columbus looks like. For many years, well, not many years, a couple of years, I guess, this was the space station concept that was studied by a number of contractors under NASA contract to look at concepts for the space station. And this, in fact, was the model that inspired the drawing that's on the front of the Engineering Week handout that you all got. This was called the power tower configuration. And as you can see, the modules, or the, let's say, the living and working quarters for the crew were down at the far end. Up at the top, the bottom in your orientation, were instruments to look at the sun or to look at stars, or in some cases to look back at the Earth. This is a better configuration from the standpoint of being able to see in a lot of different directions on the space station. Much better than the more compact ones we looked at earlier. The problem with this one, quite simply, was that it did not provide a lot of acreage, if you will. If you talk to a realtor, they'll tell you the three most important things about real estate's location, location, location. Well, this one did not have very much location, didn't have much space for hanging instruments or hanging other modules or growth and so forth. And the second thing wrong with it was, if you can imagine where the center of gravity of this thing is, it's somewhere along that 400-foot long center keel, or that center spar. The requirements for a space station include some fairly strict microgravity requirements. You've heard about people wanting to grow crystals and purify pharmaceuticals and all sorts of things. Well, in order to do that, you need zero gravity, or at least as close to zero gravity as you can get. In this configuration, since the center of gravity was somewhat removed from where those laboratory modules are located, you got a pendulum effect. And so the swinging of this long, spindly tower actually induced microgravity fields in the working modules that were greater than what the scientists could tolerate. So this concept, although it's the one that most people are most familiar with at the present time, is not the current concept. This is the current concept, and I'm sorry I don't have a better picture of it than that. But you'll see here immediately that the primary objection that I wrote, that I told you about for the other one, are solved here. First of all, the modules are located at the center of gravity, or very near the center of gravity. And with this racetrack arrangement around the outside, you have a lot more places to put instruments that want to look up, down, or out. And in this case, you see a lot of the instruments clustered on the top beam there. That isn't necessarily the only location. And of course, if you had an Earth-looking experiment, and if you were oriented in such a way that these modules were in the line of flight around the Earth, then you'd want to mount that on the lower beam, like you see that one extension going down. The solar arrays, of course, out to either side are symmetrical. Therefore, if we need to grow the station, more power is required. It's easy to add solar arrays to either side, and the whole thing stays balanced. The size of this thing, as opposed to the 400-long single power tower concept, is about 300 feet on a side. So I think that's something on the order of an acre or so footprint in the sky. It's a pretty big thing. One more thing I'll point out here. Since this is not a solar-oriented spacecraft, in other words, it doesn't always fly so that the sun is shining directly on those solar arrays, there's a requirement to develop joints that allow the solar arrays to pivot both like this, in and out of the screen, and like this, around a joint. And that is one of the contracts that Ball won, to design what's called the alpha and the beta rotary joints for those solar arrays. And we have done that. We did it under contract to McDonnell Douglas, and I'll show you a little more about that later. Let me zoom in just for a minute on the top part of that. If you can imagine now, we're going to do a zoom onto what those instruments look like on the top. This one I borrowed from our friends at Boeing. I take from everybody equally. You can see here a couple of mounting concepts. Maybe I should point a little bit here. Is it easier if I point here or up there? Okay, let me do it here. You see the mount on the end. Now this would be required, for instance, if the mounting structure that's used to mount an instrument to the end of to the spar itself would be larger than what could fit in the shuttle bay. And that seems to be the case. NASA would like the dimension of this bay here to be 5 meters. Well, 5 meters is bigger than what you can put in the shuttle bay, which is 15 feet, in an unassembled condition. So you would have to construct some sort of a little standoff device in order to mechanically attach an instrument that took up the whole shuttle bay diagonally onto a device like this that was a 5-meter bay. So that's what you see here at the end. And you see the remote arm here grabbing onto maybe that's a free-flying platform, which I'll talk about in a few minutes, that needs some servicing. Let's see. It's a little hard for me to see, but there's an astronaut right here. You see him working on some sort of a power box there. It's also attached to the main spar part of the space station. Here's another one over here. So you get an example, get a feel for the size, some of the problems with how do you bring power across that sort of interface, and communications, and how do you get rid of the heat, let alone the mechanical problems. This is Ball's primary area of concern with space station. We are under contract to define what's called the payload attachment equipment. The title of this chart, PAE, is being defined by RCA and by General Electric, and Ball is a subcontractor, RCA, to define that device. Now that segment of the presentation is what I would normally give to civic groups, sometimes to grade school, high school groups,